Anton Ryabtsev, and he's going to talk about error accumulation in conjugate gradient methods for degenerate problems.
Yes, thank you. Good afternoon, everyone. Let me introduce myself. My name is Anton Ryabtsev, and I am a MIPT student. So the topic is the error accumulation in the conjugate gradient method for degenerate problem. So we consider the task of minimizing the quadratic form function, and we make some changes of vector b. We add the noise to this vector, such as the difference between the clear vector b and noise vector b should be less or equal to exact delta. And we use the method conjugate gradient methods to solve this task. So they have three concepts of noise. The first is constant noise. This means we just change a little bit the task and solve the exact task. The second is antagonistic. So in each step we change vector b in the adding some noise depends on the sign of gradient. This means that the minimum of new function will move the direction where gradient will go. So this means that the minimum will run from our gradient. And the third is stochastic noise. This is with just add or minus the delta with probability 1/2. So we consider here we can see the results. The yellow points are the argument residual. So it depends on the size of delta. Here I consider big delta from 1 to 10, and you can see the dependency is linear. So the next is the function residual. This is something quadratic. And also I consider the bigger deltas from 0 to 100, and this is still linear, but this is quadratic also, and this is quite obvious. So let's move to the stochastic noise. Here you can see the big deltas from 0 to 100 also, and this is still the linear, and the functional residual is still quadratic. The interesting thing for stochastic method is that here you can see the graph. The blue line is the trajectory of clear function. Clear, I mean the start function with exact matrix A and exact vector B. And the red line is the trajectory of a noisy task. But we should understand that how exactly I build this red line. I just save the points, I mean x, on each step, trying to solve the noise task. And finally, I use this x to calculate the value of exact function. So this means that we don't need to average the values on oscillations you can see here. We could just take the smallest value, and this will be the best one. And the most interesting thing is that sometimes red line could be below the blue line. This means that we found the point x in which the value of exact function will be less than the value of this function on the x we found trying to solve the exact task. So this means that we could solve the exact task even better using the, for example, using the stochastic noise than if we solve just exact task. As you can see, argmin of function of points found in the stochastic task could be better than the solution of exact task. The most strange thing is we can get solving antagonistic noise task. As you can see, this could be quite good, also linear. And on the bigger noise, this could be also linear, and this is really good. But sometimes this could be strange. Something like this, or even like this. The blue line is the attempt to build the line using a least squares method. So in this situation, we can see two different lines. From delta from 0 to about 30, and from 30 to the 100. But this was the one exact task, exact matrix A and exact vector B, and vector B was changed each iteration. And this is really strange. This is I think we should research more careful. And altogether, you can see that the first picture is about the constant noise. This is quite good. We could find the solution less than for n iterations, where the n is the linear size of matrix, I mean the dimensionality. And the third stochastic noise is also good, and this could be even better than the solving of exact task. But we still don't know how much iteration we should make to get the asymptotic, to arrive to the asymptotic, I mean to get the solution with 100% belief. And the second is still the worst, but this graph let us believe that if we make much more iterations, here as you can see is 600,000 iterations, so this is much more than the size of the task. But if we make much more iterations, this could be this could maybe give the best results because the function is something like 1 over logarithm n. So the more n, the better accuracy we will receive. But this is hard to calculate it because even here we can. Even here I made very much iterations, and it's really hard to calculate, and it takes a very long time. So it's hard. Thanks for your attention. If you have any questions, I will be glad to answer it.
We have plenty of time for questions. So, questions? Maybe I have one. So you show a couple of cases when you have bad behavior.
Yeah.
So was this bad behavior due to the function that you use, or like was this because f that you chose an f that is bad, or is it just stochastic? Like sometimes it happens. Like, can you explain something a little bit?
So okay, exact this is for example the task all these calculations on each delta is about number 3, A number 3, and B number 3. And for example, this is about A number 2 and B number 2. So the differences between this picture and this is in the matrix starting in matrix and starting vector B. So I still didn't find the dependency on some parameters, properties of matrix or vector B with these different behaviors. And this is the subject to research and to better understand how does it work, because this is still not obvious, and I still don't know what's the reason of such different behaviors.
Could it be, for example, condition number of this?
No. I looked at this, and this really don't depends on condition number, because on the for example, here and here the condition number differs less than in one порядок.
Smaller than one order of magnitude.
Yeah, and I got such results on big condition number matrix, and this on small, and something like this on the big and this on small. So now this isn't obvious. This looks like it doesn't depend on the condition number of matrix. Maybe there is some other properties which could make some different, such different behaviors.
More questions?
Did you carry out experiments on some real data? Did you inject some noise into some real data and did you carry out experiments on it?
No. This is just generated by myself matrix and generated by myself vector B.
So are these matrices A's just random matrices? Each entry is like
Not fully random. This is matrix with a big condition number. For dimensionality 10, this is about 10 millions. Condition number is something like this. For 100, for n equal 100, this is about I suppose 100 millions, something like this. So I just took the smallest eigenvalue, the biggest eigenvalue, and I take the other eigenvalues, bigger, smallest. The other eigenvalues are near these values, to leave the big space between these groups empty of eigenvalues. This leads to longer convergence, as I understand. So this case is worse than if we just take the smallest, the bigger, and other between them. So I just take eigenvalues and build the matrix by them.
There are more questions? So let's thank the speaker.
Thank you.